Hello, and thank you for joining us for the very first installment of the Adaptive Education series, which has been designed to help you produce consistent, high-quality, patient-specific 3D printed RT accessories. This installment provides an overview of additive manufacturing, more commonly referred to as 3D printing, and consists of 5 parts, each focusing on a specific 3D printing technology that is available for use in radiation oncology. By the end of this series, you'll be able to define additive manufacturing and understand how it relates to creating patient-specific accessories in radiation oncology. The RT community is primarily focused on Fused Deposition Modeling, or FDM 3D printing technology to this point. However, other technologies are at or near the forefront. To that end, a comparison of common 3D printing technologies such as FDM, SLA, SLS, and jetted printers will be reviewed in this series. So what is additive manufacturing and how does it relate to radiation oncology? The AM process has produced research advancements in many different industries, including medical applications. Well-known applications include patient-specific surgical models, implants and prosthetics, dental molds, tissue engineering, and of course, the fabrication of custom accessories for radiation therapy. We'll start out in part 1 by talking about one of the most common 3D printing technologies and the one you're most likely familiar with, and that is Fused Deposition Modeling, or FDM. Due to its low cost, relatively high resolution, and multi-material printing capabilities, FDM printing has had the widest adoption of 3D printing in the consumer market and specifically in radiation oncology. So how does FDM printing work? Well, it involves a spool of solid material called filament. When this filament is heated up, the extruder places the melted filament down and builds each part one layer at a time from the ground up. As you can see in this illustration, blue filament is fed from the spool into the extruder, which uses a torque and pinch motor system to feed and retract the filament by precise amounts. From there, a heater block melts the filament to a specified temperature and forces this melted filament out of the heated nozzle, which has a specific diameter. The printer head then extrudes the filament material according to pre-programmed positions as specified in the 3D printer slicing software. The most common use of FDM printers in radiation oncology are for printing bolus, both simple or uniform thickness, and modulated electron bolus, as well as surface brachytherapy applicators. Even though FDM is the simplest out of all the 3D printing technologies, the resulting prints satisfy radiological criteria like print homogeneity and spatial accuracy. 3D printing patient-specific bolus on FDM printers allows users to produce these accessories in-house at low cost and relatively quickly, typically under a day, using various rigid and semi-flexible materials. In addition, FDM printers offer relatively large build volumes, which allows users to print large bolus in one piece, such as a chest wall. Now, let's review the advantages that FDM printers offer in printing RT accessories. First, these printers are relatively inexpensive to purchase and maintain compared to other 3D printing technologies. FDM filaments are also inexpensive and come in a large variety of both rigid and semi-flexible materials. The printers are available with larger build volumes, which is key to printing large accessories in a single piece. Spatial fidelity is maintained, particularly with rigid filament like PLA or polylactic acid, and similarly, homogeneous prints can be achieved, which is an important requirement when creating patient-specific 3D printed bolus. FDM technology is supported by simple mechanisms that are more user-friendly than other print technologies. They are easy to set up and require only basic training to use and maintain the machines. Printer problems are simple to diagnose compared to other technologies and thus result in shorter downtimes for the printer. And finally, these printers can fit into smaller spaces, requiring less real estate in the clinic or hospital. FDM printing does present its challenges, however. Every element of the printer is based off a motion system, making it simple, however, potentially failure-prone. FDM filaments currently available on the market do not offer biocompatible options, at least so far. Flexible filaments possess some level of flexibility, however, their softness is limited compared to other printing technologies. And if not maintained or set up properly, poor print homogeneity can be evident, thus requiring frequent printer maintenance. Another common 3D printing technology is stereolithography, or SLA. This technology is the oldest form of 3D printing. However, because it recently expired key patents and developments made in the materials used, it is becoming more and more accessible. The key principle in SLA printing is that it uses a liquid resin, which is cured by UV light. After a single layer has been cured, the build plate with the model is moved upwards by the distance defined by the layer height parameter. An SLA printer is made up of several components. A UV laser is mounted on a motion system. This is used to cure the resin. A mirror directs the beam towards a resin bath. A resin vat with a clear bottom holds the resin and allows the laser light in. And finally, the resin or photopolymer is located in the translucent resin bath that hardens when exposed to the UV light. The first step in SLA printing is bringing the print bed down to the initial most inferior position. The layer height is defined by the distance between the build platform and the bottom of the resin vat. The layer is cured by scanning or moving the laser to draw an image throughout the layer. After one layer is cured, the print bed is raised by one layer height and the process is then repeated. Similarly to FDM printing, bolus and brachytherapy applicators are easily printed with SLA technology. A key advantage is superior homogeneity, as this technology is not based on material extrusion, as well as SLA prints have a much smoother surface. Another difference when compared to FDM is the choice of very flexible materials, which are often comparable with superflat. Thus, printers offer the possibility of direct printing soft boluses. A key limitation when it comes to printing bolus and surface brachytherapy applicators is limited print size due to small build volume. That said, we are witnessing a rapid development of larger build volume SLA printers, some of them being validated at Adaptiiv at this very moment. SLA technology can also print intracavitary and interstitial, or IC and IS, brachytherapy applicators. Unlike FDM printing, biocompatible resin is commercially available. However, the applicators must be printed in 100% infill. The benefits of SLA printing are widespread and have proved a viable option for use in radiation oncology. SLA printing is useful because of its high accuracy in terms of print spatial fidelity, and the homogeneity of prints offer a superior solution to comparable methods. SLA technology has a very simple motion system, meaning that it has less chance of mechanical failure. And there are a large variety of resins, ranging from very flexible elastic resins, clear resins, and even USP Class 6 biocompatible resins, which enable the use of IC or IS brachytherapy applications. The surface finish of SLA prints are smoother compared to FDM prints. And finally, cost of SLA technology is decreasing over time, and advancements are evident unlike any other technology. However, SLA printing does have its downsides. Additional post-processing is required after the model has been printed, meaning that there are some additional steps to getting a print ready, including washing off any uncured resin and using a curing lamp to complete the process. SLA technology is sensitive to environmental factors. For example, external contaminants can cause some issues with this printer if it gets into the resin, as well as the optical system within the machine. SLA technology requires delicate handling, meaning there is more need for additional PPE when post-processing, and the uncured resin is a skin irritant requiring gloves and safety glasses to properly handle. Our testing has shown that warping can also occur even for rigid prints, which can cause a poor fit on the patient. And even though costs are lowering, this technology has higher material costs compared to FDM, costing almost 10 times more for even the most basic resins. And finally, SLA printers tend to have smaller print volumes due to the nature of this technology. However, build volumes are generally getting larger over time. A subtype of SLA printers emerging on the market are DLP printers. These printers are very similar to SLA with one difference: the curing mechanism. Rather than a narrow UV beam, DLP printers project a large beam of UV light in the shape of a print layer. This allows for significantly shorter printing times, which can be a significant advantage when it comes to your everyday clinical practice. Adaptiiv is currently working on validating a DLP printer and aiming to provide a fast printing solution to our customers. The next part in this series covers a broad class of 3D printers which are using jetted 3D printing technology. Those printers use a resin similar to SLA printers and deposit it in a similar fashion to FDM. In general, jetted printers are a hybrid of FDM and SLA. The input material is in the form of liquid resin, as is in SLA. After the material is deposited or jetted from the nozzle, it is cured by UV light. In this case, after a layer is deposited, the print bed is moved downwards and the next layer is started.
PolyJet is a 3D printing method that makes beautiful, precise models in a huge variety of materials and colors. It works like an inkjet printer, but instead of jetting drops of ink, PolyJet 3D printers jet tiny droplets of liquid plastic. A UV light instantly cures the plastic, solidifying it. And so, layer by layer, complex models take shape. The most advanced PolyJet systems can build multi-material parts. Soft, rigid, clear, and colorful. You can even adjust material properties like heat resistance and durability. The same technology that makes gorgeous prototypes also makes precise manufacturing tools. Designers can predict future needs and serve them now. Manufacturers deliver better products faster and with less waste. Researchers have new methods of saving lives. PolyJet is reshaping industries like film, fashion, and medicine. It's helping people with great ideas improve the future. What's next?
Research into using jetted technology is becoming more mainstream in the industry, and Adaptiiv is actively working on validating this technology for use in radiation oncology. Our research thus far has shown that jetted printers are able to produce bolus accessories with sufficient spatial accuracy, as well as satisfying homogeneity requirements. Printers come in various build volume size, enabling printing of larger bolus in a single piece. And another difference when compared to FDM printing is the choice of flexible materials, which are often comparable with superflab. Thus, jetted printers are also offering direct printing of soft boluses. Also of note is that the printers are capable of producing highly accurate surface brachytherapy applicators, but similar to SLA technology, those applicators must be printed in 100% infill only. And another advantage of jetted technologies, similar to SLA, is the presence of biocompatible materials, enabling the application of IC and IS brachytherapy solutions. Another rapidly evolving area of jetted printers are proton range shifters and immobilization devices. Similar to SLA printing, we have found that jetted printers offer superior homogeneity, which is a requirement for proton range shifters. We at Adaptiiv are currently working on employing jetted technology for 3D printing immobilization devices. Large build volumes and the use of strong materials result in immobilization accessories being printed that are highly stable. Another application of using jetted 3D printing technology is to create anthropomorphic phantoms. Phantoms typically involve larger volumes requiring a significant quantity of material. Jetted printers offer the possibility of 3D printing in various colors and are an ideal solution for producing anthropomorphic phantoms. Using jetted technology has a number of benefits. First, it's highly accurate and has very high resolution, with advertised dimensional accuracy of plus or minus 0.06%. There is a wide selection of materials, including a flexible material with variable softness and biocompatible materials. Jetted printers come with various build volumes, enabling different applications according to the specific needs of a clinic. And similarly to SLA printers, resulting prints have a smooth finish, but jetted printers offer the capability of printing in multiple colors. Jetted printers also offer the opportunity for additional clinical applications, such as surgical models and surgical guides. These areas don't fall within what we do at Adaptiiv, but are widely used across the world. Although this is a well-rounded technology, there are some downsides. Currently, the biggest disadvantage when it comes to using jetted printers is the price tag. These printers and its resin are more expensive than any other technology that we've discussed. Second reason is supports in post-processing. Because this technology suspends resin, it requires a lot of supports or else it will flow downwards. Removing the supports is a simple process, however, it will require adequate PPE as the materials involved are caustic. Finally, these printers take up a larger footprint than any other printer discussed and tend to be noisier as well. The last technology that we will cover is SLS printing, or selective laser sintering. SLS is an additive manufacturing technique that uses a laser as the power source to sinter powdered material. In principle, this technology is different from the others as it uses powder material as its input. Before each layer is printed, a roller deposits a layer of the powder, which is then cured by a focused beam. After that, the build plate moves downwards and a roller applies a new layer of the powder.
Once the nylon powder is loaded in the supply container and digital instructions are programmed, the laser unit directs a high-powered beam to a reflective mirror. From there, A galvamotor system steers the focused beam to the powder surface. Each layer of part geometry is then sintered into a heated bed of nylon. Pistons move the supply container up and the build chamber down, while a roller moves across the bed to distribute the next layer of powder. Excess powder is captured in a collection container. The process is repeated layer by layer until the build is complete.
SLS printing has huge potential for the RT industry. Application for bolus and surface brachytherapy applicators is yet to be investigated, but there is potential to obtain a comparable print quality to the aforementioned technologies. In addition, proton range shifters are an option, as is the potential for immobilization accessories. Research in this area will likely increase as this technology becomes more mainstream in the industry. Now, let's talk about some of the advantages of SLS printing. Because this technology has the model completely submerged in the material throughout the print, this technology does not require any supports. SLS printing is known for its highly accurate technology and tight tolerances. In addition, it primarily uses a nylon-based material which has robust mechanical properties. It's capable of printed parts with hinges and joints and can print very challenging geometry. Disadvantages of SLS printing are that it's relatively expensive, although it's becoming more accessible as new companies invest in the technology. With printing accuracy comes slow print times, this being the slowest of any of the technologies that we've discussed already in our education series. The cost of material is high. Having a reservoir next to the printer build volume limits the build volume to half the total volume of the printer. Adding the other required mechanisms makes this a rather large printer compared to the build volume of the machine. Post-processing can be messy, and finally, this technology has only one rigid and one flexible material to print with. Now let's review what we've covered in the education series so far. There are many different types of 3D printing technologies available, some which we've covered here, but not all are created equal. The good news is that many are suitable for printing radiation oncology accessories. There are several factors to consider when deciding what 3D printer to use in RT, such as budget, what you intend to use the printer for, and the level of technical experience that is required of staff. FDM printers are affordable and can be used in a variety of applications. The printers are simple to use and are suitable for beginners. Also, FDM printers come with larger build volumes, so you are less limited in terms of the size of the accessories that you can print. On the other hand, SLA printers are becoming more widespread as they have comparable build volumes to FDM printers and are ideal for users who want to pursue intracavitary or interstitial brachytherapy solutions, or those who want to create superficial accessories. Jetted printers are a significant investment, but on the other hand, offer a variety of applications for different departments in the hospital, such as surgery. Finally, SLS printers are ideal for printing very complex geometries, as those printers do not employ any supports. We at Adaptiiv are working very hard to ensure that different 3D printing technologies are available to our customers. We hope that this summary of technologies and our update on our research is helpful when considering what printer works best for your center. Thank you for joining the first installment of our Adaptive Education series on additive manufacturing and uses in radiation oncology. We look forward to seeing you again in the near future.